Hello everyone. Welcome back to the ICSI Atlantic time band. We are about to have this session for our third keynote. Session is going to consist of two parts. First, Jane and I are going to announce some of the awards. Then after that, we are going to have Peter O'Hearn present his keynote. So here is the list of the awards that we will announce. First, we'll have Distinguished Paper Awards for the main technical track. And then we are going to give some information about the other awards. In a physical conference, we would like to invite all these chairs and award winners to the stage to actually be recognized and receive their awards. Unfortunately, in this virtual format, we cannot easily do that. But we are thankful to all these chairs for the help that they've provided in selecting these awards. Moonju Kim, Willem Visser, Xin Yu, Sungwon Kang, Amy Ko, Tim Menzies, and Leandro Minko. I'll give the stage now to my co-chair, Jane, to talk about the process that we followed for selecting our Distinguished Paper Awards and to read the first few ones.
Hello, so we're very happy to be able to announce the ACM 6 Distinguished Paper Awards, and we wanted to explain a little bit about the selection process. As you know, we accepted 129 papers, and ACM 6 allows us to choose 10% of these to award Distinguished Paper Awards to. So we had a nomination process in which program committee and program board members made nominations for the best paper, Distinguished Paper Awards. And then Darko and I, the co-chairs, selected the following 10 papers. So it's our pleasure to announce the awards now. First award goes to A Tale from the Trenches, Cognitive Biases and Software Development by Suti Chattopadhyay, Nicholas Nelson, Audrey Au, Natalia Morales, Christopher Sanchez, Rahul Pandita, and Anita Sarma. We're going to hold all of our applause until the end, but congratulations. The second award goes to An Empirical Study on Program Failures of Deep Learning Jobs by Ru Zhang, Wenkong Zhao, Hongyu Zhang, Yu Liu, Haoxiang Lin, and Mao Yang. The next award goes to Big Code, it's not equal to Big Vocabulary, Open Vocabulary Models for Source Code by Raphael Michael Karampatis, Hlib Babi, Romain Robes, Charles Sutton, and Andrea James. The next award goes to Context Aware In-Process Crowd Worker Recommendation by Yunji Wang, Ye Yang, Song Wang, Youngjae Hu, Dandan Wang, and Qing Wang. And the next award goes to Here We Go Again. Why is it difficult for developers to learn another programming language by Nishel Shrestha, Colton Botter, Titus Barik, and Chris Parnan?
Okay, thank you, Jane, for presenting the first 5 awards. I will read the next 5. We apologize if we mispronounce some of the names of the award winners. Next award is Time Travel Testing of Android Apps by Zhen Dong, Marcel Bem, Lucia Kojokaru, and Abhik Roy Chowdhury. Congratulations. Next one, towards the use of the readily available tests from the release pipeline as performance tests. Are we there yet? Zishuo Ding, Jinfu Chen, Wei Shang. Translating video recordings of mobile app usages into replayable scenarios. Carlos Bernal Cardenas, Nathan Cooper, Kevin Moran, Oscar Chaparro, Adrian Marcus, and Denis Poshivanik. Unblind Your Apps, Predicting Natural Language Labels for Mobile GUI Components by Deep Learning. Jieshan Chen, Chunyang Chen, Jian Changxing, Shiwei Shi, Liming Ju, Guoqiang Li, and Jinshui Wang. And the last one is White Box Fairness Testing through Adversarial Sampling by Peixin Jiang, Jingyi Wang, Jun Sun, Guoliang Dong, Xinyu Wang, Xingang Wang, Jinsong Dong, and I think. Congratulations to all the winners of the Distinguished Paper Awards. Can we please have a round of applause?
Okay, congratulations to all of you. And one thing, if you can just go back one more slide, Darko, for a second. One thing Darko and I were really pleased to notice in the set of awards this time, that they really covered a diverse set of our ICSE topics. So they're from all different areas, and we were pleased to notice this. So now we'll move on to the other awards. And it's my pleasure to announce the IEEE Software Best Software Engineering in Practice Paper Award. So this is awarded to the best paper in the Software Engineering in Practice track, and is supported by IEEE Software. So the awardees this time are property-based testing for LG home appliances using accelerated software in the loop simulation. And that is to Mingyu Park, Hun Yan, Taeyun Byun, and Yundya Choi. Congratulations. The next award is for the New Ideas and Emerging Results track. It's this Distinguished Paper Awards, and they have selected 2 papers for this award. Is Your Quantum Program Bug-Free by Andriy Muransky, Lei Zhang, and Javad Daliskani. And the second one, To Predictive Constraint Solving and Analysis by Ilyas Almawi, D. Medini, Kagdas Yellen, Milos Gligoric, Sasa Misalovic, and Safraz Kershid. Congratulations. And then in the Software Engineering Education and Training, the Distinguished Paper Awards, again, awarded to 2 different papers, presenting and evaluating the impact of experiential learning in computing accessibility education, to Yasmin El-Glali, Weishi Shi, Samuel Malakowski, Chi Yu, and Daniel Kurtz. And finally, We Should Teach Our Students What Industry Doesn't Want by Kevin Ryan. Congratulations. Okay, and I'm not going to read all of these ones, but we also have, there are also a number of awards given for Distinguished Artifact Awards, and some of you may have just visited the Rose Festival and seen all of the great work that various people are doing in encouraging our community to create artifacts associated with all of the papers, whether they're quantitative or qualitative. And you can see here, although I'm not going to have time to read all of these, you can see the many different people that have invested time creating artifacts that were judged award worthy. So congratulations to all of our Distinguished Artifact Award winners. And then moving on, we also want to thank the distinguished reviewers from the technical track. Again, we're not going to read names here. We mentioned these in the plenary session. We have 6, first of all, we should say giving awards to distinguished reviewers is always a bit tricky because so many reviewers give so much time and do such a great job. But these ones just stood out. And congratulations to our 16 distinguished reviewers. And also this ICSE and a couple of the last one as well, we've used reliable rapid response reviewers, which are reviewers who agree to just jump in at the last minute and help with reviews if we have a last minute need. And they were just amazing. And so thank you to all of those as well. So let's congratulate all of our award winners across all of the tracks. And let's everybody give them a round of applause. Okay, thank you. And I'm going to hand back to Darko now.
Okay, thank you, Jane. Congratulations once more to all the award winners. We appreciate the work that you've done. Sorry that we just could not bring you all to the stage to acknowledge that, as would have been done in a typical physical conference. We are going to proceed now with the keynote. So our speaker will be Peter O'Hearn. My pleasure to introduce him. So Peter Ahem is a research scientist at Facebook and a professor at the University College London. He's been doing research in the broad areas of programming languages and verifications for over 25 years, having held academic positions at Syracuse University, Queen Mary University of London, and University College London, before joining Facebook in 2013 with the acquisition of the verification startup Monadix. He has worked on separation logic, theory which opened new practical possibilities for program proof, including the technology which led to the Infer program analyzer developed by Peter's team at Facebook. Infer runs internally on Facebook code bases, detecting over 100,000 bugs which have been fixed by Facebook developers in the past 5 years. That's why our Facebook does not crash anymore. Peter will be talking about that, how Infer is also used in production at a number of other companies, including Amazon, Mozilla, Spotify, and Marks and Spencer. Peter is a fellow of the Royal Society, a fellow of the Royal Academy of Engineering, received a number of awards for his work, including the 2016 Gödel Prize, 2016 CAV Award, and 2011 and 19 Popple Most Influential Paper Awards. Peter, the stage is yours.
Great. Great, thanks very much for that introduction. So, I mean, it's a real pleasure and an honor to be giving this talk, and I wish we could be doing it in the beautiful city of Seoul at the moment, but given that we can't be doing that right now, I'm really grateful to the organizers for pulling this together. So I want to talk about, the title is Formal Reasoning and the Hacker Way. What do these things have to do with one another? Well, for most of my career, I didn't have any touch with software engineering, which makes it a real special pleasure to be talking at this conference. And before 2013, these are some of the things I was working on. There's a denotational semantics paper. There is a separation logic paper. There is concurrent separation logic. And finally, around 2009, I get into academic static analysis. My postdocs and PhD students dragged me kicking and screaming into static analysis, but really my research was on formal reasoning. So I'm going to talk, formal reasoning, and I'm going to talk about this thing, the hacker way. So what's that? What does the formal reasoning have to do with the hacker way? Well, there's the hacker way. So the hacker way happens to be the address of Facebook's office, but this isn't what I actually want to be talking about. I don't want to be talking about the address. Rather, in 2013, something strange happened. So I was working with this startup company, a formal verification startup company, and we got acquired by Facebook. And there's the leadership team, which is myself and the CEO, B. Lavender, and Dino DiStefano and Cristiano Calcagno, two other founders, at the Facebook office. When we talked to them before they acquired the company, and we were about to get on the flight back to London, and it was very clear that we were going to have an offer in place by the time we got back to London. And my colleagues there are looking very happy, you see, and I'm looking maybe a bit uncomfortable. So why was I uncomfortable? Well, I knew a lot about formal reasoning, and here I was on the Facebook campus, and there's hack again emblazoned on the floor of the main quad. So it's not just the words like hack that had me a bit worried. It was after I landed at the company, then I saw what was going on inside in terms of the code. So here I was steeped in formal reasoning, and let's make a slogan for formal reasoning: move slow and break almost nothing. And Facebook had other slogans at the time, like move fast and break things. And so I wasn't just worried about the slogans, but here we had tens of millions of lines of code, and not only lots of code, but the code was changing extremely rapidly. Over 100,000 commits per week. This was back in 2014. There's a lot more. These numbers are a lot bigger now. So now if I measure that against how we usually think about program verification, like write the spec, write the program, laboriously prove the program, and then celebrate, then it looks like this might be a problematic situation. So I was, oh, how's this going to work? So luckily, the size of the code wasn't a problem for us, because we had worked on a program analysis that led to that startup company. And the program analysis was compositional. And I want to explain that. That comes from the denotational semantics. It worked independently on different program parts. And this enabled the program analysis to scale to the tens of millions of lines of code, no problem. So we got into the company. And what I did is we hooked up our program analyzer and ran it over Facebook's Android app for apps for first. So there's Messenger, and there's Facebook, and now there's WhatsApp. So various apps, there's Instagram. We ran it over those, and we trained the analyzer, and we worked really hard to get control of what everybody in the program analysis field had told me was the most important thing, the false positive rate. So we worked really hard to get the false positive rate for this particular code base down. So I thought the false positive rate was pretty good. I thought it was around 20% or under. Then we switched the program analysis on. We switched it on and we ran it overnight in what I'll call a batch deployment mode. And then we shipped the bugs to the programmers. We assigned bugs to programmers, expecting that they would fix them. So since there was a low false positive rate, we were ready to accept congratulations and celebrate, except that nobody congratulated us. We were met with silence. So hardly any of the developers fixed any of the bugs that we reported. They weren't paying attention. And I was like really worried at this point. I mean, I thought, oh my God, we've just come into this company and brought all this research. Maybe this isn't going to work. And this caused sleepless nights. This caused me much more stress than I ever had as a professor, because you're staring real failure straight in the face. So this caused some sleepless nights. But as happens when you're in a challenging situation, we didn't give up. So while this was going on, the batch deployment mode, we were working on another deployment. And so more important than the big code is the huge number of commits per week. And we had this thing, the compositional analysis, which can work on program parts instead of the whole program. You know how when you run a compiler, then you change one file and recompile. If you're lucky, it's only going to recompile that one file instead of the whole entire program. So the program analysis was running like that. This meant that not only could we handle the big code base, but all these many commits, we could process them all fast enough to keep up with the pace of change, because we had this thing, the compositional analysis. A linear time whole program analysis would have been no good in this situation. We had to have the incremental analysis for it to work at all. So we were doing that. We were doing the incremental analysis. Then, this worked in a very interesting way. So this will be the only separation logic that you will hear in this talk. So separation logic codifies a principle of locality, so that you can run a program proof only over little bits of memory and then extend it to big memories. So it only needs to talk about the little bit of memory that a program part uses instead of the entire global memory. And then things are stitched together by the inference rule, the frame rule. So our program analyzer was running over all the different commits to the code base. And in each case, this rule, the frame rule, is picking off just enough memory to reason about each parts of the code base. So it was working, but we were still in this problem where previously nobody fixed the bugs when we showed the bugs to them. But then something happened. So there's the deployment model was more like this. So developer makes a code change. Then in the continuous integration system, a version of Infer is sparked up. It runs on that code change and not the entire code base. At the same time that that's happening, human code reviewers are making comments on the code, and they're shipping those comments to like a social media for code review, which is called Fabricator. And eventually, maybe Infer finds a bug, it participates as a bot in that code review. And then finally, the code is shipped to product. And so it would make, we would automatically make comments on the code review system like this one. And so we would do this for a number of different bug types. So the stunning thing that happened was this, and I wasn't prepared for this. So you remember the batch mode deployment had almost nobody fixed it. Let me say it was a 0% fix rate. Then this other deployment of the same analysis had a diff time, this diff time continuous deployment had a 70% fix rate. I remember the day when one of the team members told me when we got in the morning, oh my God, Peter, our fix rate is over 70%. And everybody was stunned. We weren't prepared for this. I had always heard things like, it's better to give signal earlier than later, but never had I seen any numbers like this. This completely floored me. And the other thing that this gave me, my first lesson, was that this was for the same analysis in FIR, deployed in two different ways. So the same analysis had the same false positive rate. So this told me that it wasn't true that the false positive rate is necessarily the only or the main determining factor for the effectiveness of a program analysis. Speed matters, and speed matters a lot. And so the developers told me many interesting things about this. I went around the company and I gave talks saying, this is what happened, what do you think? And the developers would laugh when I told them about the batch deployment. They said, that will never work. And then when I explained the diff time deployment, they said, this is why it works. Several reasons, but one of the reasons was the cost of context switch for the human brain. So when the developers are in code review, right, and the programmer is in code review, and they find a problem, the mental context of the code is swapped into their brain. And so then when the program analysis tells them a problem there, then it's all swapped in, and they're ready to understand it, and they're ready to act and fix it. Then in the batch deployment, what they have to do is whatever they're doing, like consider, suppose you're doing a mathematical proof, or you're doing an some form of exercise, and then somebody comes and they say, do you want to fix this bug in some code that you don't know or that you've never seen? That you would have to learn that code, you would have to swap it in, and maybe you could fix it. You could decide whether you would fix it or not, and you would have to give up what you were doing before. And that's extremely expensive, as we know as humans, this human cost of context switch. So the diff time continuous deployment solved the problem of context switch, and it worked together with the developers in their workflow. And I never thought about this beforehand, but the developers told me many stories like this, that this is why things will work. If you deploy in a way that works with the software engineering process, then it will be much better than if you deploy in a way that's outside of the software engineering process. So if the analysis adapts to the programmers, it's going to be much more effective than if we want the programmers to adapt to the analysis. It's a two-way street, but that was a really big lesson. Now, so that brings us to the hacker way. So I was getting into the hacker way. So the hacker way, this is in Zuckerberg's letter to investors before IPO. The hacker way is an approach to building that involves continuous improvement and iteration. So this continuous improvement and iteration was part of the whole culture of code review and checking for things and in CI that was going on, and where we hooked in to this process, then we were embracing the hacker way, whether we knew it or not at that time, and that worked out quite well. Now, one thing is for the program analysis team to work with the programmers and the programmers' way of doing things. We ended up developing our program analyzer in this way as well. So this was very interesting. So usually we would, before this experience, we would try to get rid of all the false positives or most of the false positives and then turn on a check. What we ended up doing is we ended up shipping checks to the developers earlier before we knew they were perfect. And then the developers would tell us what was wrong with them, and we would iterate with the developers to get to a better solution. This was really great. This let us not ship checks that the developers didn't like, if they would tell us early, and it enabled us to get to the better solution quicker. So I remember one time there was a null pointer exception false positive, and I jumped on it. I jumped on it, and I was interacting with the person that we had reported it to, and I was apologetic, and the person said, no problem. This is a false positive, but you've saved me time on other cases, and thanks very much for the tool. So they see that if we're with them, we're working with them in their fast, iterative way, then they'll forgive us mistakes. That's the move fast and break things. The break things is more like, try to do good, but improve, and we will forgive your mistakes. And we found that the developers would forgive our mistakes as long as we were responsive and working with them. So this was, I mean, this was a completely different way of developing software compared to what we had done as academics, which was to try to make it perfect and then ship it out the door. So we developed it, the Infer Program Analyzer, in this iterative way ever since, which is quite an interesting thing. And so, so the story I've given so far, there's a CACM paper, recent one that tells that story, and there's another paper. Now I'm going to dive into some detail on analysis hacking, how some of this works, right? So I'm going to talk about an analysis that I developed with some other friends on the team myself. And the context is, so I was the manager, I was a theoretical computer scientist, then I went to Facebook and I was the manager of the team. I was the manager of the team for a few years, and then I started to get antsy because the tool was successful and I wanted to do some technical work. So I stopped being a manager and I moved to the engineering or scientist track, and I started to do technical work. And I was wondering what to do, and I was talking to my manager at the time, and I said, well, the hardest thing I can think of to do in program analysis is concurrency. So I need to get my enthusiasm for this, so why don't I try to work on that? And I had said this to Mike Hicks, who was on the SIG plan executive. I had said this just before I started that project, how I wanted to do things like make an analysis that could scale to many programmers and many programs and not get in their way too much. And this seemed like a pretty hard thing to do when I said it. And so at the bottom of the slide, I'm just reminding you of why is concurrency hard. So there's enormous numbers of interleavings, right? If we have a few instructions, then very quickly, if we look at all the interleavings, we get to the number of possibilities are more than the estimated number of atoms in the universe, right? So there's no way, even with the fast computers, to get after concurrency by exploring the interleavings. So this was hard. And part of the backdrop was as follows. So there was a very important, this is representative of static analysis for concurrency. There's an important paper by Engler and Ashcroft, which was one of the early static race detectors. And they had found 3 race bugs in Linux. And Linux is big, and that's a great paper, I would say, but it's not a lot of bugs found. And we can believe that there are a lot more bugs than that found. Now, people worked on static analysis for concurrency for a while, and it was begun to be thought in the community, it's not easy. It's not necessarily going to work very well. And so this was motivation for people to work on dynamic analyses, like thread sanitizer is an impactful in practice dynamic analysis for race detection. And in the thread sanitizer paper, they will say one of the motivations for doing this, and in the precursor papers, is that the static has been found to be very difficult to get impact out of it. So not to be dissuaded, I said, right, okay, so I'm going to go after static, right? So, and why would you want to go after static when you've got dynamic? Static tends to be a lot faster. I can deploy it at diff time and catch bugs a lot earlier. And I catch different bugs than dynamic usually, but it has complementary benefits to the dynamic. It's not neither better nor worse. Anyhow, I thought I'd have a go at that. So during this period, I spent, instead of starting hacking on the tool, I was trying to understand the engineering context. I thought, well, let me find out what Facebook's concurrent code looks like. This was Java code, and see what we could do to help the people. So I had this thing in my back pocket, which I thought would help me have an in to doing static analysis for concurrency where it was so difficult up until that point. And that's this theory concurrent separation logic, which we won't get into in any detail, but I had that in my back pocket. And I was confident, somewhat confident, maybe crazily so, that I could make some progress there. So I started looking at the code and doing mental proofs in this program logic about the code to understand it. And I made 3 discoveries in this time. It's important to scope the problem before getting going on it. And scoping the engineering problem was great because I found there was no explicit thread spawning in the code. It was all done by, quotes, framework code with spawning all the threads. This was important because I had spent a couple of weeks on making a pencil and paper algorithm for analyzing thread spawning, but it turned out I wouldn't need that algorithm. So it's always good when you can not need something in a program analyzer because it's so difficult to make an effective one. So cutting away the problems is very important. But we found this thread safe keyword sprinkled in places, and I took this as a goal to show thread safety should at least mean that the methods, when run in parallel with one another, don't race with one another. I took that to be an approximation of the concept of thread safety. So why don't we make a program analyzer that can check for that, check for data races on these thread safe classes. The second discovery I made was my theory, concurrent separation logic, could easily reason about all the examples I saw, all of them that I saw in the code base. And they weren't only easy examples. There was some fine-grained locking, and there was examples like this that the developers are trying to minimize the use of locking for performance reasons. So in this case, this was a comment in some Facebook code. This is written to by the main thread with the lock held, or read from the main thread with no lock held, or read from the other state with the lock held. So the idea here is I've written it in a sort of pseudo Java notation there. If the lock is held, then if I assign to X under synchronization, that won't race with the subsequent read from X because they're on the same thread. But it might race with the parallel read from X. So I need to synchronize the parallel read, but I don't need to synchronize the one in the same thread. It's saying things like this. So this avoids us having extra locking that we don't need. And so I won't go through that proof, but there's a program logic proof in concurrent separation logic there. Very neat proof was working, showing that there was no races in this code. So this was looking really good. This was looking really good. So the final discovery was synchronized. This was by far the most common construct. So this is important too, because it says sometimes there could be two locks in a file used at the same time, but very, very seldom. So as an engineer, maybe that's not the first problem although for the perfect solution, you need to deal with that. Maybe that's not the first problem to mount, right? So I didn't mount that. Again, it's good to cut away the problems because you're still gonna have difficulty. So then in this period, I developed an algorithm for solving this race detection problem. I ignored multiple locks and I began my implementations, and it was all going well. It was all going very, very well. Then, so I had a grand plan. I thought I was going to ship in 1 year, and I thought I was going to find hundreds of bugs compared to the paper, say, by Engler and Ashcroft, which I repeat, I consider a great paper, but they found 3 in Linux. I thought, I'm going to find hundreds of bugs, and I'm going to prove race freedom for thousands of classes. And so to my way of thinking, this would have been impact far beyond static race detection before, and it would have been with a beautiful prover. So this seemed like a good plan to me, and I was very excited about it. And I didn't have any concrete results, but the management was happy because it sounded like a good plan. Then this intervention happened. My colleague Sam Blackshear on the Infer team, he was working on Android, and he used to make posts to all the Facebook Android programmers once a month or so, or maybe once every 2 months, saying what we were up to. And then at the end of his post, he said, there's also a fancier concurrency analysis in the works, the one that I was working on. And he did this without me knowing. I didn't say, Sam, would you please tell all the Android programmers that I'm working on this thing? He just did it. And the first thing the Android programmers asked, the first comment to Sam's thread was about this thing that I didn't know was going to be revealed. And this, will the eventual thread safe thing be recursive? This was their way of saying, will it be an interprocedural analysis? That's the way we would talk about it in program analysis. And the reason is, sometimes people think that you can just get away with simple checks within one procedure all the time. But you can't. This has loads of false negatives if you try to do that. And this is a good example. Android, they were trying to take Facebook's Android app, right? It was single-threaded. They were trying to move it to a multi-threaded context. Now, Android UI is arranged in trees like UI. Now, one class per node in the tree. Turns out the mutations happen near the leaves of the tree. All of the races would be interprocedural. None of the races would be gotten by a within one procedure race detector. So the first thing they asked for was an interprocedural analysis. That was quite interesting. Now, this scared me because I had been working on this thing, and I had my beautiful prover that I thought would come out in a year. And So I just didn't pay too much attention, and I just kept working. I kept working, right? I kept working. And I just wanted to get my prover out the door in about a year. But then more messages started to come my way. So here's a message from, this was a manager in New York by the name of Jay, I think that's Jason, yeah. Jason in New York was working on this team trying to convert the Android app to a multi-threaded context. And he said, hey, Peter, I'd love to talk about it and how it could dramatically help us in each one. That's the first half of the year. And so do you have time to chat? And I got other messages of this variety coming my way. Now, so at this point, I had a decision to make. Could I say, nope, no can do, I'm not going to talk to you. I've got my plan. I've got my beautiful prover. I'm going to stick with it. See you next year. They would have been done by next year. Or I could have said, well, maybe I should change my plans to try to help these people. Maybe when I was a scientist, I would have said, I need to complete my beautiful prover. But when you're working in the engineering context, the first thing you have to do is you have to help the people, right? So I couldn't put them off. I had to drop it and help. And not often also do you find products teams coming to you and saying, please, please help. Static analysis team, please, please help. You don't often find that. And when you find that, that's like gold. So I said, okay, time for me to change my plans, time for me to adapt to the engineers rather than the engineers to adapt to me. So with a somewhat heavy heart, I had to give up the goal of my prover. So we made a specification of a minimum viable product with the Android team. And the specification wasn't dreamed up by me. It was done by collaboration between people on the Infer team and people on the Android programming team, the Android newsfeed team. It was done by collaboration, trying to find something which would be useful to them and that we could get to them within 2 months, or so we thought, so we could help them in this project of transitioning the app to the multi-threaded context. So the first point was no need to provably find all the races. So no need to be a prover for absence of bugs. Now they would have liked that. They actually asked for that, but I said, I can't give you that in 2 months with an acceptable false positive rate. And they said, well, that's not the main thing. We have to make the call whether to check the code in. We want you to advise us. And so they said, so we'll take that over taking nothing at all. There's the other points. Another important point at the bottom was treatment of coarse-grained locking, but not fine-grained. So the first thing an academic scientist like myself, or a scientist would want to go for in concurrency is, let's go over fine-grained locking, non-blocking concurrency, hand-over-hand locking, all this very interesting stuff. Don't go after that. That happens in just a couple of classes that experts deal with, concurrency experts deal with. There's thousands and thousands and thousands of classes that people who are not thinking about concurrency use and can get things wrong as far as concurrency goes. Help all those people before you help the experts. So they said that. So I went again against what I would have done when I was an academic scientist. I would have gone after the technically difficult but infrequent problem. They said, don't go after that. Go after the other problem and handle it very well. Okay, so we went after that. Okay, so we made a program analyzer. I won't go into the details of the program analyzer. There's some lattices, right? It's what's called a compositional abstract interpreter. So it's got some lattices there. And rather than talk about let's do with programs, let's talk about programs instead of math. So there's this comment from before. There's the idiom which avoids races. So it's about not always locking on the main thread, right? And so the things above the line here are all safe with respect to one another. So the unprotected read on the main thread on line 8, that's no problem. You know, we've got this write on the main thread on line 6. It's no problem with that because they're on the same thread, right? Now, the protected read off the main thread, that's the thing that can run in parallel. And when we're off the main thread, we have. So the ones below are problematic, right? They're problematic. So there's a race between these two. We have a protected write off the main thread, but that can race with an unprotected read on the main thread, you see. And then there's another problem there, right? And so our program analyzer finds these races and it makes a report like this. The report says that one of these methods is in a read-write race with the other. And what it's doing is it's like in English saying what the lines are showing there, and it's giving a reason for the developer. So it does that. An interesting point is how it does this. So it does this by what's called a summary-based program analysis. So for every procedure, we make what's called a summary. And the summary is like an approximation of the denotation of the meaning of the procedure. And so in this case, it keeps track of information about threads, information about accesses, and information about locks held. So in this case, the race between these two, we computed a summary for the first of the procedures, and you see the read in blue and the write in blue at the bottom. They conflict. You see the threading information, the parallelism in brown. Parallelism is not excluded by that. And then you see the true and the false. One of them's protected and the other's not protected. So so what the analyzer does is it makes summaries for the procedures completely independently of their context. Then it looks at the summaries later to decide what the potential races are. So it does this, and because it works like that independently is what allows it to scale to the big code and to run fast at continuous diff time. Okay. So the impact that we got from putting it in deployment was 2.5K, 2,500 concurrency issues were detected and fixed. So if you compare that to the earlier number of 3, I guess that seems like a pretty good number. There are false negatives. So there are bugs that it misses, especially I can make them up very easily. But a strange thing that I wasn't expecting was running this thing for a year in production. None occurred that we knew of that were reported back to us in production. Although it has false negatives, it was remarkably effective. And that surprised me. So that was good. Engineering comments were like this. The thread safety violations are useful because they help to catch nasty and hard bugs. Concurrency is hard, and developers really like a program analyzer that helps them with concurrency. And so you see there's huge wins in terms of scroll performance. So the static analyzer helped us get wins in terms of performance, which is really an important thing to have. And the best quote, one of the engineers said, without infer, multi-threading in newsfeed would not have been tenable. So they wouldn't have been able to do the project. So it's not just that we found bugs, but we enabled a positive engineering project. So this was, you see, the impact that we got out of this. So I had my beautiful prover, and that made me feel good, or that I was aiming for. But then by giving up on that, we ended up actually with much more impact than I ever dreamed of at the beginning. The impact here far outstrips my grand plan, right? It's really, really stunning to me, the good things that can happen when the scientists or the technical analysis folks talk to the engineers in a deep way and work with them on their problems in a deep way. It's really remarkable what can be achieved as far as that goes. Okay, so you might think that I'm happy about this. So as an engineer, I'm happy about this. Right? As an industrial employee, I'm happy with this. As a scientist, I'm very unhappy about this because I had to give up my beautiful prover. So we started getting to react. We started, well, let's try to convert this thing to satisfy a quote soundness theorem like static analysis to make ourselves feel better, right? So one of the team members, Nikos, implemented an alias analysis to catch more bugs. Even though at that point we didn't know that there were no false negatives in practice. He did that. What happened? A blizzard of false positives ensued, and we couldn't turn the alias analysis on in practice. Sam, another team member, implemented an escape analysis to try to catch more of the false negatives. Again, too many false positives, couldn't put it in deployment. My favorite was take my old thing, the concurrent separation logic prover, grow it, and then do a switchover. But we couldn't really do that because that prover was getting a little bit better, but the gap was growing. The in prod analyzer was moving away from it. The gap was growing, not shrinking, so that wasn't working. And then one day, I said to myself, stop this. Stop trying to prove this standard theorem, which is going to give you a worse analyzer. Stop this. The analyzer might not be wrong. Maybe the theory is wrong. Try to prove a theorem which corresponds to the good analyzer, prove a different theorem, rather than changing the analyzer and making it worse in order to satisfy the theorem that everybody else would want to prove. So we proved this theorem called the true positives theorem, which is that under certain assumptions, the assumptions are related to product code, but not infrastructure code that we found at Facebook. Under certain assumptions, there were no false positives. So when I stated the theorem at first, it was false, and it only became true for an idealized analyzer after a long time. But an interesting thing is it influenced design decisions in the analyzer. Like, we had something called a deep ownership hypothesis, which is that if I assume that x.f is owned in the sense that it can't leak to the outside, then so is x.f.g. So this is actually false in code. But if I build that assumption into the analyzer, then I get extra false negatives, but I don't get extra false positives. You see, that was consistent with this theorem. Once we had this theorem, we felt justified in making decisions like that made the theorem more true. So an interesting point here is that theory is used not to bless the analyzer afterwards, but it's used to help develop the analyzer when it's in flow. That's when a theory is much more powerful when it does that, rather than just blessing later on. So that worked out quite well. And this wasn't completely pretty, all of these theorems, but we were starting to get into a direction where the engineering experience is starting to influence the analyzers. So last part of my talk, so we started to do that. So I started by describing how we got in touch with this thing, the hacker way. Then I spent the last while describing how I hacked an analyzer, right? I was responsive in the development of the analyzer rather than dreaming it up beforehand, and how this helped a lot. But I was irritated as a theorist by the result, even though it was very effective. So this made me think, oh my God, there must be some theory missing. So maybe we should go back to the beginning and look at the theoretical foundations of all this stuff. So now it's time to hack in the theory. So this is about a paper in Popple in Correctness Logic. And the basic idea of incorrectness logic is this. So there is Hoare's triple. Before, the states beforehand, it's a pre-post spec. You run the program, and if you terminate, then those states after are true after. So this is great. You see, it's expressed in terms of post conditions. The post condition of executing the program on before is a subset of after, the set of states after. So this subset inclusion is responsible for false positives. So if I see that false positive, that's the bit in after that's bigger than the post of before, right? That's responsible for false positive. That's called over approximation. Now, what if I'm going to say, I don't want any false positives? And I want to do this purely logically, just in foundational terms. I'm not talking about running the program, although I will, or I would, but just thinking in terms of the math. Then what we want to do is we want to get inside the black. So let's do this. Let's take that subset symbol and let's try to get inside the black instead of outside of the black. So let's move that up and let's move that out. Bring in, it's inverse. Oh, wow. Then we've got inside the black. You see that? And then let's change the notation because we've changed Hoare's triple. So there's some prior art here. There's a nice paper by De Vries and Kudevas who defined this notion with an equivalent but different definition, but they didn't connect it to bug catching. And you could have defined it in terms of this theory dynamic logic from a long time ago. And you could have defined it actually 5 seconds after Hoare's logic appeared. You could have done that. Now, let's try to see what this triple means. It actually takes some getting used to. So here's this triple. PCQ means if Q is it means the Q is a subset of the post of P. Now beforehand I have Z is 11, and I'm going to execute the program. So then afterwards, you see the assignment of 42 to Z. Afterwards, we have 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 42 to Z. that z equals 42, it under approximates the states reachable by executing this program, right? Well, when I've asked this, you aren't all present, but I've asked this in many talks. Everybody has gotten this wrong for some reason, though it's not actually true. It's not actually true. There's an assignment. See, suppose z is 42, but x is 1 and y is 2. You can't reach it from the beginning. You can't reach it from the beginning because that if x is even, if y is odd, if x is even contradicts the x being 1. So z42, x1, y2 satisfies z equals 42, but there's no way to get there from the pre-state. Ah, so that's very interesting. Everybody gets that wrong. Why do they get that wrong? Because I think it's not because they know Horde logic, it's because humans have wired into their brain without knowing it, this rule from Horde logic, which lets you make the drop conjuncts as you go forward. That's a rule of Horde logic. Let's look at this a bit more deeply. So what you would have to do is you have to record more information to get a correct under approximate conclusion. You have to record more information. So this is very interesting now. So there's Hoare's rule that doesn't work for under approximate reasoning. Here's what's called the rule of consequence. Now in normal Hoare's logic, the implications are in a different direction. You see what we're allowed to do when we're reasoning about under approximation? If Q is an under approximate conclusion of C, and I make it smaller, then it's still an under approximate conclusion. So I'm allowed to shrink the post, right? But I grow the post in normal correctness reasoning. In incorrectness reasoning, I can shrink the post. I can do the opposite. And although this principle just falls out from the mathematical definition of triples I gave before, although I wasn't looking for this fact, if you think about it, this kind of thing occurs in concolic execution engines like Dart and Clee. When they partially concretize the state, this can be seen as an instance of the principle of shrinking the post. Another consequence is where you don't have that rule of Horde logic at the top. You have this rule of the incorrectness logic at the bottom, which says you can't drop conjuncts going forward, but you can drop disjuncts. Oh, what does that mean? So disjuncts are used to reason about different branches of an if statement, right? So this means, thinking in terms of program analysis, it's okay to ignore paths. Now you might think, heart be still, right? Heart be still. Peter is a bad person. Ignore paths. Unsound, right? Unsound program analysis, right? No. I'm going to be a good person, and we change things around so the kind of thing that program analysis people would like to do, and that humans do when reasoning about the presence of bugs, is declared sound like it should be. So far from being a bad person, I'm going to try to be a good person and use under approximation to help people. So this principle, you can drop paths, is implemented in this program analyzer inside Facebook. There's the lead developer, Jules Viard, and it's an analyzer for C++ lifetimes. And he did an experiment for me where he had the 20 disjunct limit versus the 50 disjunct limit. So what this analyzer does is it keeps disjuncts of facts about memory. And when it got to 20, it wouldn't add any more to the abstract state. So that's like the forgetting paths that I just showed on the previous slide, the sound proof principle. He compared that to 50 disjuncts, and he ran the experiment. Now, it turned out that the 20 disjuncts case found 97% of the issues that the 50 disjuncts case did. So 97%, but it went a lot faster, 2.75x wall clock faster. So now you might still be thinking, oh my God, bad person, what about that 3%, right? But no, this gives the engineers a dial to turn to help people in different ways. So I could consider doing this. So maybe I run the 20 disjuncts case at diff time, at code review time, on every commit, every pull request submitted to the code base, I run the fast one. Then only periodically, I run the 50 disjuncts case to catch the extra 3%. And so that's going to let me help the developers faster in their workflow the vast majority of time while not missing the extra 3. So you see, turning these things up, soundness for having a pure over approximation wouldn't let you do this, but having under approximation lets you play this kind of game that can help people. And this kind of thing not only allows the analyzer to keep up with the people, it can save time in the data center, it can save energy for the planet, and so on. So that to me is great to have that kind of flexibility. So there's a general point here that for correctness reasoning, as you go along a path, you get to forget information. You get to make the state bigger. This is the principle of abstract interpretation. This is called abstraction, making the state bigger. But you must remember all the paths, and this is the difficult part in over approximate reasoning. For incorrectness reasoning, as you go along a path, you need to remember all the information, or you'll be unsound for incorrectness, but you get to forget some of the paths. So you see that it's not that one kind of reasoning is better than the other kind of reasoning. They're complementary, and they have different strengths and weaknesses, and each of them has different room for maneuver when you're implementing a tool. That's an interesting point. That I didn't know this. In retrospect, it's sort of obviously true, but it came out as a consequence of those mathematical definitions, which is quite interesting to me. So the final bit of code that we're going to talk about is a loop. So you see this loop 1, the Kleene star, in line 22 and 23. That's Kleene star means execute x gets x plus 1 some number of times and then exit. We don't know how many times. Now look at the first achieves one assertion on line 19. That corresponds to bounded model checking, unrolling the loop 4 times, right? So one of the conclusions can be x is 0, 1, 2, or 3. Maybe it's 3 times. Now, bounded model checking, unrolling it 3 times is not enough to prove that you've got a bug in the client down there, right? Because there you need to unroll it 2 million times to get the error. What if I said if x equals 4 million? Oh, then I would have to unroll it 4 million times. What if, so I don't know how many times to unroll it beforehand, right? What if x equals n, where I don't know what n is? Then I don't know how many times to unroll when I do loop 1. So bounded model checking is a great thing, but it has its limitations. Now, it turns out that x is bigger than or equal to 0 is a sound under approximate conclusion of the loop. It's also more succinct than the bounded model checking one. And x is greater than or equal to 0 as an under approximation is enough to conclude that if x equals 2 million, then that error can occur, right? So as long as I know that that's a correct post condition for loop 1, then I can get the error. I can't get that assertion using bounded model checking. So there's a tool, CBMC by Daniel Cronin et al. That does some of this kind of stuff, tries to guess strong assertions to get you past under approximate assertions to get you past loops. Now, how am I going to prove this? This is very interesting. So this thing, the under approximate triple, says that every state in the result is reachable from some state in the presumption. So you think of that in terms of a loop. It's like a liveness property executing backwards. So if we think about what liveness properties were like, that eventually something will or can be reached, then the way of reasoning about those in Hoare logic is to have what's called variant functions. You find something that goes down. So the Hoare logic way of reasoning with loop invariance is not sufficient for proving these kinds of properties about programs. But we want something that goes down, but we want it to go down in the backwards direction to reflect the backwards way of reasoning about this. So there's a proof rule, the backwards variant rule, which is like this, which says, I'll just say it in words, to reason about a loop, you need to find a quantity that goes down in the backwards direction. To reason about its reachability properties, its under approximate reachability properties. Now, back to this code. So there's a way to prove this code where what I select for my P of n in that rule is that x equals n, because going in the backwards direction, it's x that's going down. And it turns out that using this, I can prove this property of the loop, that x is bigger than 0 is a valid post condition. And therefore, I can prove that that error is reachable without executing it or unrolling it 2 million times. Now, there's also a completeness result that I have, which says that any loop has one of these backwards variant things. So I can prove all of the loops relative to some, you know how because of Gödel incompleteness, we have some problems about proving everything. So relative to some things there, relative to an oracle for deciding various stuff, we can prove all the loops. So that's very, very interesting. So what I wanted to do, I wouldn't be surprised if I lost some people there. So I wanted to start with the engineering, the experience of interacting with the engineers. Then I wanted to talk about analysis hacking, about static analysis people interacting with engineers. So that was the analysis hacking, making the program analyzer. And then finally, theory hacking. We're actually finding new theory for under approximation here, which is motivated by all of that experience. Now, this new theory is being implemented and being informed by several analyzers at Facebook. There's also a sense in which the under approximate program logic, there's a sense in which it has testing as a special case. I don't say anything bad about testing there, rather something good. Years and years ago, Dijkstra made the remark that testing is good for proving the presence of bugs, but not their absence. And unfortunately, whether he intended it or not, some people took this as license to poo-poo testing. And this has always really bothered me. And the people working on logic and theory didn't pay as much attention to testing as they should have done from my point of view. I acknowledge work on symbolic execution and things like that. I acknowledge lots of good work. But I always thought there should be more foundational work there. And the fact that this has the testing as a special case of the under approximate triples is only a good thing. Now, okay, it has that, and it has several analyzers we're working on. I think that there's a lot of potential in this theory that's coming out of the practice, and we don't know exactly where it will lead, but there's a lot of potential avenues to follow. So I'm pretty excited about that, and a number of people are as well and are working with me on that. Now, the final thing I want to say, though, is what an amazing experience it's been for me. Going into the company Facebook, being completely terrified of engineering, not having done any myself, learning from so much from the engineers that changed the preconceptions that I had as somebody working in program analysis. From the academic side, I had wrong preconceptions. And then finally, creating new theory as a result of that experience. So my opinion is that, at least in program analysis, it's a great time to be working in industry, because we've got this situation where if you just try to do if you just try to do engineering only and don't pay any attention to the theory, then I think you're not going to get the best results. But if you just do theory and you don't pay attention to not only the engineering of the analyzers, but the engineers, the product engineers, if you don't pay attention to them, then you're possibly missing out on a lot of opportunities for generating new concepts and new theory. So working in industry has been great for me because I get to play these things off in a tight feedback loop at one moment. So, okay, so thank you for listening. This concludes.
Okay, thank you, Peter. Can we please get a round of our applause, the virtual one? Sorry, we are not there in person to clap, but we do have the playing of that. Thank you very much for your interesting presentation. We do have a number of questions that have arrived here. So I will first start from these ones. So first one is discussing a bit more broader context, as companies like Facebook face challenges beyond the software correctness, such as privacy and fairness.
Hang on. I need to listen to. I need to turn up the volume.
Sorry, do you hear me now?
Just a sec.
Okay.
I'm sorry. Go ahead. Yes.
Okay. So yes. So the question says companies like Facebook face challenges beyond software correctness, such as privacy and fairness.
Yes.
What role can formal analysis, maybe more specifically static analysis, play for these types of properties?
Well, you know that privacy is related to information flow. That's not everything about privacy, because people have to, there's policy decisions, but there's lots of technical work that can and should be done by program analysis people, both static and dynamic, as well as language design people, that are completely relevant to the privacy problems. And I don't know if I should reveal exactly what's going on, but that's just because I don't know what's been made public. But there's lots of people, programming language kind of people, working on these kinds of problems in the company that I'm in, and presumably in the other major tech companies as well. So yes, that part is very relevant. And did you mention bias or fairness?
Fairness, yes, that was the part
Yes.
of
I
the
mean,
question.
there's sort of beautiful work on this. I think it's Cynthia Dvork, I think it's her name, and other people have made beautiful mathematical definitions to do with bias and fairness in algorithms. And there are people in our company who certainly know a lot about that. And I think, you want to apply this to AI algorithms, and people are probably definitely thinking about that. And static analysis, there's good academic work on that by Auzal Barghouti has done fantastic academic work on that, and some other people. I don't know if that's scalable enough to be applied to the kinds of code bases that you find in the major companies at the moment. But going forward, I see, it was a good question. Thank you for the question. Because going forward, I see this as something where people with the kind of skill sets that you find in program analysis are relevant to these kind of central concerns of big tech companies. So yes, very relevant.
Thank you. Before I go to the next question that's in the panel, you mentioned AI, so maybe a more general question. Will we be able to use AI to replace some of the static or dynamic analysis and just subsume it completely?
Yeah, that's very interesting.
Go ahead.
Oh, sorry, go ahead. Did you finish the question?
I want to say the dual of that is, can we use static analysis to analyze the AI systems?
People are really working on static analysis to analyze the AI systems. There's great work by Vetchev and company there, and other people. And AI people want that. In particular, AI is a kind of programming, right? Development of AI models is a kind of programming. And it needs the kind of CI, continuous integration style of deployment, just like programming does, but some things play out a bit differently. Now, can AI replace static analysis? The history of AI is, as soon as things are understood enough, they stop calling it AI. So all the stuff we're doing in static analysis was called AI one day in the past, right? Like our static analyzer infer has a solution to the frame problem, which was one of the first AI problems. It has a solution to abductive inference, which is a classic AI problem. This is from symbolic AI. And so it's already, in that sense, it's already in our program analyzers. It's already in there, but we just don't jump up and down and say we're doing AI, but we were doing stuff that would have been classified as AI decades ago. And then I think maybe the questioner is wondering rather, can we take the more modern probabilistic AI to replace it? I don't really think so, because there's a lot of people have worked on that, but the results haven't been very impressive so far, to my way of thinking. And the way my way of thinking is like, you have to define the search space, and then these AI agents can get through the search space pretty good. But defining the search space is very hard, and that's where we need the humans. And so I don't really think of it like that, like AI is a magic bullet that's going to replace everything. I don't think that that's a very realistic kind of approach. It's good to use techniques being developed in AI. It's very good to do it, but to do it with open eyes and not expect magic to occur. That's my opinion anyhow.
Okay, thank you. Yeah, so the question about AI is typically nowadays about this probabilistic or statistical, not symbolic reasoning.
So I answered that, I think.
Let's see, the next question here, I think one disappeared from this link. So it's sorted by upvoting and downvoting. So the audience can, say which question they would like to have asked. It says this, so your first part of the talk has mentioned how you learned this lesson that giving feedback to developers early is better than giving it later, or giving feedback on commits is better than on the old code.
Yeah.
So this is a lesson that may have been mentioned elsewhere, say in software engineering community before. So maybe a question is, how could have that message been communicated better, or what paper would you want to read to find that out?
Before too. I had heard it before too, but I had never heard it to the 70% to 0% degree. And so it's one thing to hear it in the abstract, and somebody says it's good to give messages earlier. I had heard that many, many, many times in the abstract, but then when I got the 70% to 0%, it's like it slammed me in the face, right? It slammed me in the face that just how big that was. And so it's like I said, it's to software engineers, it wasn't a surprise. Like I said, when I went around the company and told the story, the engineers would giggle at me for being so naive. But rather, the program analysis community hasn't taken that on board. And the program analysis community has been doing whole program analysis. For the vast majority of program analysis papers are whole program analysis, which even if they were linear time, wouldn't be able to work on the commits on a big code base. So, this is the learnings of the program analysis people like me getting smacked in the face about our program analysis problem. As far as general goes, I think engineers know it, and computer scientists have heard it, and software engineers aren't doing anything wrong by that message not being out there. Maybe certain sub-communities, if they had been more into the engineering, they might have heard that better. So the fact that it's known in the software engineering community, I just agree with. And I wouldn't say that you've done anything wrong with the messaging there.
Okay, thank you. Next thing, also, think in terms of software engineering. Ask what role, if any, did requirements play in your work, or maybe in general in Facebook engineering? Does anyone write down some kind of formal requirements? Is this always informal in developers' mind? Did that somehow shape the kind of properties you were checking in your analysis?
Yeah, the thing is, our analysis very often checks things that are generic errors, like race condition. They can be defined for any program, so that are independent of requirements. The requirements might be softer, like we need to make the program faster and we need to make it concurrent, right, for it to meet the goals. And then that leads on to race conditions being a problem. But this whole iterative development approach, it's been hard to make that work. As far as listen, the people I'm talking to know more about software engineering research than me. But from what I've seen in my part of the industry and in let's call it big tech, the idea of write the formal requirement that then survives as code is mutated rapidly to the hundreds of thousands of times per week, as is happening in all the big tech companies, I think that that's a difficult one. And so I think that what I see is that informal requirements are good and they're done when they can be. But it's hard to keep up with the pace of development. To see this idea, I'm not saying that the questioner is thinking this, but a straw man idea is, oh, let's write the formal requirement first and then write the software. That's the water flow model. And I'm not saying that the questioner was suggesting that, but that's the water flow model, and that's a very impractical way to go about doing software engineering. So there's that, the pace, but then there's the attitude that for some of the things we don't know what we want until we give it to the people, right? And so not necessarily for the back-end infrastructure code, but for some of the requirements will be sort of hard, like privacy requirements. But some of the requirements about how we present things to the people might not be like that, or a new feature that's going to be put up on Facebook or Messenger or something like that. It might be better to experiment with people and see. And so I think that the whole idea of the iterative software development, there's probably some buzzwords about that, but the iterative software development is that we write the software to learn, partly to gather data and learn what we want. And that doesn't mesh all that well with the idea of thou shalt write this requirement in the first place. So you might find this funny coming from me, since my background is in formal reasoning and logic. But I want formal and reasoning and logic to be able to adapt with the programmers, and to ask them to write that requirement beforehand is very, very tricky. I wasn't able to do it for my own program analyzer. So.
Okay, thank you. Some follow-up here. I don't quite understand. It asks if there are any properties that are requirements, not just customer requirements, maybe just ask some properties that must hold. Not sure that I understand the question myself. Also, I just want to tell you there is some lag. What we discuss now here, the audience actually hears in about 10-15 seconds. So yeah, it's a bit of lag from when I get the sub questions.
No problem, no problem. So I think that, are there any things that must hold? Well, let's put it like that. I mean, we've got tens of millions of lines of code. Nobody's ever proven tens of millions of lines of code, so we don't know that stuff holds and must hold. But it would be good if certain things were true. Well, yeah, it would be good if there were no buffer overruns. It would be good if there were no pointer exceptions. There's, loads of things where it would be good. And you know, the difficulty of the must is making it so. So yeah, there are, and besides those, there are going to be others. There are loads of things that really should be true in the ideal world. Yeah.
Okay, thank you. Maybe moving on to the next question. It asks, how can one incorporate analysis hacking or theory hacking in their research without access to a big company or maybe a lot of developers? You just mentioned as a part of your previous answer how getting this feedback for developers help to shape your agenda, to prioritize your work, to know what should be done or shouldn't be done, what matters or not. How can basically academics do that? They don't have access to so many developers.
That's a great question. And I mean, I am cognizant of this fact that what could be severely irritating, and what used to make me severely irritated, was when an academic goes and becomes an industrialist and then says, you should be like me, when the academics don't have access to all of the resources and the situation of the industrialists. So I'm not sure that the academics, okay, program analysis people I'm sure of, I'm not sure of software engineering research in general, okay? People shouldn't aspire to do things like the way that I'm doing it in the industry, because you can't get access to the developers. So I think what you can do, though, is people can see that there are problems coming from the several people who are working in the industry and then feeding the information back to the academia instead of only in the other direction. There are technical problems and research areas which need to be mined, which have not been. And so this thing I keep coming back to is the incremental program analysis is so much more powerful and useful in practice than the whole program analysis. And yet the vast majority of the subject is working on whole program analysis. So I would love it if there was a shift in balance where more people worked out the foundations and the algorithms for doing the faster incremental program analyses and understanding some of the trade-offs. I think it's almost it's a totally unexplored space almost. Our team finds are making decisions to do this or that to our algorithms. We don't know what will happen. It's not been mapped out in the subject because so few people have worked there. So that, and there will be other things. I would say paying attention to the problems is the best I can say, but I'm absolutely not saying that the academics should behave like the scientists who are embedded in industry. What I really like from the academics is working on fundamental problems, which might be a bit longer, have a longer horizon than is usually the case in industry, because we don't want to be duplicating work. We learn from the fundamental work in program analysis. In software engineering, like I don't know, I'm not up on all the software engineering, but say the work of Parnas and Dijkstra and Hoare and people like that about modularity back in the 70s. Absolutely fundamental work has a huge influence, right? So fundamental work of that variety, I think, has a huge impact. And for me, I would think the academics should concentrate on the fundamental work as much as possible and not be too apologetic about it. And just to pay attention to what goes on in the industry as seeds for the problems that you might work on.
Okay, thank you. Well, I have now two things going on. One thing is in the chat saying that for academics, maybe hard to get funding for longer term or fundamental work. How to convince the funding agency to deal with that. If you want just a brief comment, kind of putting your academic hat on to answer about that. Will Facebook pay? Would Facebook fund such research? Go ahead.
I'll respond to that. So my answer there was just saying how I think that the academics should behave, quite apart from the constraint of funding. Now, it is true that the funders in some countries want the academics to behave more like industrialists. So I will just think that I think that that's a mistake, right? I think that it's a mistake on the funders' part to want that. And I think for society, it's better if the scientists behave like scientists and not try to behave like industrialists without all the funding of the industrialists. So I think that that's a mistake, and I think that it's better to stick to your principles about going after fundamental work. But I acknowledge the difficulty in getting the funding for that. So I don't have an answer. I just saying what I think is the right thing to do.
Okay, that's fine. Thank you for that. Yes, there was a follow-up comment whether Facebook would pay for long-term research, but I know that there will be a meeting with Facebook after this in the third hour, and there is also the presentation later. And I know that you are running some of the calls for research proposals. Let me switch to another topic that we had here asked in Slido. It follows up on what you discussed, that maybe academics should not work much with a lot of engineers if they don't have access to them. This is the dual of that. Since you did have access to all these engineers, how did the Facebook developers react to the kind of feedback they got from the tools? Did they struggle to understand? Was there something specific about formal logic? Maybe how you present your results to them?
Yes. So I think the thing is, the first way that we would ever dream up to give them the results usually doesn't work out all that well. And so there's this approach called canarying, where what you do is you ship your product to a few people instead of all the people. And so we can talk to certain individuals who might be interested. So we don't necessarily just turn something on for 5,000 developers right away. We might share it with a few developers and get feedback. And invariably, a lot of the communication issues are debugged at that stage. I think that's a simple answer, and I think that's just a good way to approach it.
Okay, maybe I can just ask a personal question. So I'm part moderator and just forwarding the questions to you. But my interest specifically is saying something like race detection. Yeah. You know, my experience has been that when you report that to people, debugging is very, very hard. We've tried some things. You get thread sanitizer, you run, you get some reports in the just some pick up a random open source project. You get these reports, but then getting someone to actually debug that is quite challenging and hard. Not just because it's technically hard, but get them to buy that the report is relevant or important or is going to lead to the crash. Again, this is open source, quite different from Facebook app. But what's your experience with that? Say, what fraction of these race reports get addressed?
I think that when we reported our paper, 50% was the fix rate for the race reports. And that's pretty good because, you see, for easier kinds of things to fix, there's a higher percentage. Now, this concurrency, it's very hard to reproduce errors, and it's very hard to understand the source of the error. So you're right. And we could get that rate up with a lot more work on root causing that we haven't done and things like that. But it's just difficult. Like, finding the bug is one thing, understanding the reason for the bug is another thing, and then fixing it is another thing. So it's important that these things be actionable, right? And that's very difficult. And things become more actionable as a result of this back and forth with the developers, because there's various things that we can do wrong. Like, we can spam them by giving them too much information, or we can give them information in the wrong way. And so by interacting with the developers, what we do is we get rid of all the bad bits of information that we would give them. But then they're still left with the problem of actually understanding the bug and how to fix it. And it might be that the report that's been turned up is a bug that should be fixed by somebody else, right? Because it might be the root cause might be in a different area of the code. And so we don't have an answer to that. What we're doing is we're surfacing the bugs in as efficient a way as possible mentally. It's mentally efficient, we hope, for the developers, and we get there by iteration with the programmers on how to present them. But then the next stage is very hard. And I don't know any way to make it easy. And technical work can be done in that direction, but there's no way I know to make it easy. And so often it needs in some cases, what we end up with is a team between the static analysis creators and the developers. We have people who are almost product experts who understand it all deeply and who get to know how to really fix those kinds of bugs. That's happened in several technologies at Facebook, where the tech team, say the static analysis or the types team, and the programmers, there's another team in between them for handling certain of these difficult bugs. So there are strategies like that to put in place, but putting humans in the loop in that strategy right now is very important. And then the humans do create tech, but it's not just what we might think of immediately, like, oh, let's find the minimal bug trace that, some kinds of things like that. It's tech that's really specific to the engineering circumstances that people get developed for how to do code mods to fix bugs and things like that. So right now, human in the loop.
Okay, thank you. So yes, we need humans eventually. Maybe the next question then here ask about the kind of the bugs that were found and fixed. Some of your early examples were about null pointer exceptions. You just mentioned yourself that if a bug is easier to be fixed, it has a higher, presumably, fix rate, up to the point that one can automatically fix things. So if you want to comment maybe on types of bugs that you found and fixed, and maybe advertise some of your work on automated fixing from Facebook.
Yeah, so that there's work on automated fixing in collaboration with other teams at Facebook, where they're fixing mainly null pointer exceptions. So the infer program, so we've not gone that far in auto fixing. So we probably further than most, right? But infer static analyzer has something like 60 bug types, or maybe it's 40 bug types. So let me just mention a couple. There's null pointer exceptions. There's memory leaks. There's data races. There's starvation. There's deadlock. So you say we're now getting into more difficult things. Data races, starvation, deadlock. Starvation and deadlock checkers are very, very impactful. See, because when your phone stops responding, that's almost worse than it crashing, right? Because now you don't know what to do. You don't know if it's gonna, so it wastes people's time, it wastes humans' time. And so Nikos Georgianis, one of the people mentioned during the talk, has a deadlock detector and starvation detector that's been very, very impactful. And then there's performance. Ezgi Chitek, one of the engineers, and Dino DeStefano beforehand worked on this. There's an analyzer for performance, which does complexity analysis of the code. And when the complexity of a code fragment changes, it tells the developer about it. And it's not necessarily a bug, right? Because they might want the complexity to change, but it's just telling them. So they're there. Null, leak, race, deadlock, performance, or complexity are five examples of bug classes. There's many more examples of specialized and easier bug classes too. So there's a lot. But there's one thing that it doesn't have. It doesn't have buffer overruns. And this is a good thing for me to tell people about. Buffer overruns are the oldest static analysis problem, or one of the oldest, and you would think it would have been solved decades ago. As far as I know, for a static analyzer running on bare code without the programmer doing a lot of work with the annotations, so just running on the bare code, there's not a scalable solution to the buffer overrun problem in static analysis. Now, things like address sanitizer and Valgrind, these dynamic tools, are effective, but they're much slower than static, much slower. So remarkably, after all these years, this basic problem to my way of thinking remains unsolved. So we don't have a buffer overrun detector because we've tried it and we've spent some time on it and it didn't work out too well.
Okay. Now that you mentioned some of these dynamic analysis tools, actually, I can ask this the follow-up question here. You presented the work about the diff time, but tests are also run at diff time. So people do run some kind of dynamic analysis.
Yeah.
So how much is there interplay between static and dynamic analysis, or what are the strengths where they can combine each other?
Okay, so let's talk about unit tests, which are very often run at diff time. And the reason they can run fast is often because of mocking, mocking is like, and the test harnesses, which is the human is writing specs, basically. The human is doing a tremendous amount of work in order to make that run at diff time. If the human were to do that same amount of work for static, we could run a lot more static at diff time too. But now let's talk about sort of the more end-to-end kind of things like fuzzers. Those are much harder to run at diff time because they take a lot longer to run. And they have to have they're like a whole program analysis. So the interesting thing about static is it can be interprocedural. It doesn't need all the mocking, and yet it's usually a lot faster than the fuzzers. But it's not better than the fuzzers. It's finding I'm not a fuzzing expert, but the fuzzing experts tell me it's finding different kinds of bugs than the fuzzers. I don't see any reason in principle why we can't make compositional and incremental fuzzers that can run at diff time. I don't see any in principle reason for that. I'm not saying it's easy, but at this point in development, as far as I'm aware, it's mostly not, or almost always not run at diff time. So the pluses and minuses are that the dynamic doesn't have false positives, but it has false negatives. Apart from unit testing, it tends to be slow, and it's hard to work on partial programs. Those are the characteristics there. The characteristics of static are, it can be a lot faster, but it suffers from false positives. So they're complementary. Maybe we can have the best of both worlds someday. We'll see.
Okay, thank you. So let's see. The next question here I have is, if there are some developer annotations that would make your analysis easier, you obviously discussed the thread safe and kind of compositionality there. Have you had success motivating developers to add some annotations? Any thoughts of how one may go about that?
Yes. It's a very difficult human engineering problem, that one. And usually, so there's people, there have been cases, there's cases going on right now with the infer tool that I don't know if we made public yet, but there's other cases, like there's this thing called the hack programming language, which is typed PHP. And PHP was migrated, and Facebook was migrated to be almost fully typed, many millions of lines code base by this gradual typing idea. And this required, again, teams of people between the teams of people who knew the engineering culture and the code bases well enough to know that would work well and wouldn't work well for that migration. And so to just put the tech out there and say, just hope that the developers will happily annotate, it's quite difficult. I think it's quite difficult. There's loads of education that needs to be done, but there's also deep understanding of the engineering context that's needed. So we have had successes with that, very important successes, but one should never presume that there's magic bullet solutions or that it's easy. So the technical side will be more easy, maybe. The human engineering side will be more difficult.
Okay, thank you. I have a lot of questions coming up. If you are fine, we can continue.
Yeah, fine, yeah. I'm enjoying it.
Okay. So yes, so we've discussed a lot of these technical things. Someone is getting back to this issue of broader impact, kind of social things. Ask, what are the ethical implications that you wrestled with in your work? Is the technology that you develop ethically neutral, or are there wider perspectives that are important?
You know what? I feel good about the tech we're developing being used for good inside of the company that I'm at. And I'm fully confident of that. I'm fully confident of the ethical side of the way that tech is developed. But our tech is open source, and I'm not going to say that I think tech is ethically neutral, or tech can sometimes be used for bad. So it's being used for good inside Facebook. Most of the uses that I can foresee are good, but I don't want to be naive and make some general claim about that. I just don't want to do it. Okay. I think that's as much as I can say on that.
I don't know exactly what the questioner had in mind. If they have a sub-question, please feel free to add them here in chat. Just like to remind that there is this lag. I mean, I can myself, envision potentially how this technology could be used in very insidious way.
Well, I mean, it's like you can ask the same for fuzzers, right? Never mind my static analysis.
Sure. But I meant just, if I'm say, manager at Facebook, I could decide to fire someone who gets a lot of infer reports, right? If I just say, you're writing the code, static analysis finds bugs, I will not evaluate you well, or maybe things like you will have to fix the things that were reported here.
Yeah, I've never seen that. But I think that if developers were not performing, I doubt that the static analysis would be, that would be the only reason. But I'm just saying I've never seen that. One could imagine that in some world it could occur.
Yeah, so this was just kind of one of my wild kind of guesses, claims. I really don't know what the speaker had in mind.
Okay.
About this discussion with developers, I have here something on the other window saying that sometimes when you have this kind of barrier or firewall between developers and testers, you do independent verification, validation, can create very adversarial culture where these sub-teams kind of fight, or if I find bug in your code, that's my great success, it's your great loss. So is it that maybe by you being so closely embedded with the engineering team that you really create a shared value, social identity, so that maybe you're having more success because you're working closely with them, they listen more and better to you? That's
true. That's a perceptive observation, and it's true. And it's not just about the way that static analysis and testing is done at Facebook. There's culture posters on the walls, and one of them said nothing at Facebook is somebody else's problem. And so the idea is we're trying to be in this together. And when I find a bug in somebody's code, generally they're thankful. They're thankful because it makes then they can fix that bug, and then that bug's not going to occur in the wild. But the attitude is very positive and about being together. And we were never when I first landed at the company, one of the executives said to me, like, we're not going to put the clamps on the programmers to behave according to your tool. What you need to do is make your tool so good that the programmers want to use it. The programmers are the bosses, not your tool. And this was very nice. So there was no adversarial relationship there, you see. And it was a perceptive question by the questioner, but it extends beyond things like static analysis and testing. It's trying not to have walls between teams. Of course, you've got a big company of tens of thousands of people. There are hierarchies, but there's a real effort to pull down walls and blockers.
Okay, thank you. There was one question later talking about the security bugs. Kind of how are security bugs dealt with? Is it only focused on the latest commits in the diff time or on the old code? Maybe
let me say two things about that. First of all, Infer we had the 0% fix rate in batch mode in that early experiment. We do run in batch mode sometimes, and it is effective, and it's nowhere near 0% now. Diff time is better. Everybody accepts diff time is better when you do it, but sometimes we do batch now. And our team is not focused on security, but there's other static analysis teams or other teams in the company focused on security. And one of them is made a tool called Zonkalan, which is in the CACM paper that we wrote that I referenced. And that's similar to Infer. It's a compositional static analysis that can run on, in their case, over 100 million lines of code. And it does what's called a taint analysis. And it's found, I think, over 1/3 of the severe security bugs over a certain period were found by that tool. More than fuzzing, more than anything else, which is very impressive. but see, its deployment model is completely different. Like some of it's at diff time, but sometimes what they do is they take a whole batch of reports and they give it to, say there's 4 highly trained security experts in an area of the code base. They give them to those people, just those security experts. And it turns out that that deployment model can be good for security because, see, what you've got in security, you've got a few number of experts in the world. So they're hard to find. So anything you can do to save them time is good. And if they're just doing grep to find bugs, that's bad. So even if the static analysis in that case has a higher false positive rate than you might expect for other deployments, that might be okay. That might be okay for those people. So security can benefit from different deployment models than general deployment can. And I've just outlined one there, but there's a lot more information on that in the CACM paper. And like I say, I'm plugging another team. That's not our team, but I've actually learned a lot from them about static analysis deployment in the security space, which was quite interesting. And it's well worth reading that part of the CACM paper.
Okay. Thank you. So the next question even goes maybe even beyond the security, asking the question, wouldn't it be possible to do formal verification of some properties? Would there be some benefit to Facebook to try to prove some parts of the code? I have to mention our first keynote was Nancy Leveson. So she was discussing kind of completely different kind of software things, maybe in self-driving cars, in avionics, medical, kind of safety critical systems, where one really needs to do a different maybe approach to development rather than go fast and break things. So I mean, is there anything at Facebook where there would be a value for formal proof? That's the question.
There's lots, and I can't talk about exactly what it is, and I know some of it, and I've got my eye on some of it, and I'm working on some of it. But the great difficulty in formal verification is the efficiency of doing it, not whether people would like it. I've not met people against it. But there's a paucity of tools. Like let's consider this. There's important infrastructure code in the tens of millions of lines of code, say, or maybe it's more, written in C++. And you ask yourself, how many formal verification tools are there for C++? You usually end up with a count of 0, or an account very near to 0. And if it becomes 1, it's an experimental tool. So formal verification as an engineering discipline, we're starting to get there, but it's not that advanced. See, what you've got now is you've got demonstrator projects appearing in systems conferences, little operating system is proven, things like that, at great cost. So very impressive demonstrator projects, but the economics of all that, okay, economics not just in terms of money, the cost in terms of people's time is huge. And whenever you take people's time, they could have spent that time doing something else. So the great difficulty is doing it efficiently and having the tools to do it. That's a great difficulty. But yes, there are targets. And so I'm trying to change all that. But I want to communicate to the questioner that it's not a case of people are in the company saying, you know what, we don't really need that verification. It's more like, oh, that would be nice to have. What would it take to do it? And then when you as a scientist start looking at what would it actually take to do it, then you start to realize, whoa, I've got a challenge on my hands. But I'm looking into that. Stay tuned.
Okay, thank you. I guess the next question was also related. I would like also to ask the name of the speaker. Unfortunately, I only see the first initial P. Someone has asked, since we have mathematical foundation of fairness, wouldn't it be possible to do formal verification for these? And what are the challenges? I assume your answer would be very similar with scaling, but maybe you can address specifically. It seems that fairness is a lot in people's mind.
Yeah, I think it's a really good thing to do. I think that formal verification of things related to memory safety and so on is much more advanced than fairness. And even that is very difficult. It's not very advanced in an engineering sense. So the fairness bit's even less advanced. And so in principle, it seems good. In practice, how far we are away from it, probably pretty far, but you never know. What if suppose we took some people who were experts in fairness and embedded them in one of the companies and did some interesting work, they might be able to come up with some surprises. I don't know. But my instinct is that fairness is harder than the normal verification problems because it's got the probabilistic aspect, right? The definitions of fairness involve probability, and probabilistic verification is less advanced, although it's good, than the non-probabilistic verification. So it therefore seems to me like a harder problem. And so the easier problem is already hard to deploy. So again, I think it would be wonderful to do. And the advances going on in the scientific community are absolutely relevant. The engineering side is difficult.
Okay, thank you. Thank you. Yes, also engineering good UIs is important. I was just told how to find the name of the person who asked the question. So we have from Daniel Schwartz Narbonne. He's asking, how likely do you think that automatic fix generation is? Partly how valuable and how challenging is that to achieve?
I think achieving something has happened. I think the tool is called SapFix from Facebook is actually doing some of that. I think Google has some of that. How valuable it is for easy bugs, I think it's going to be pretty valuable. For the important bugs, I don't know. It's all to play for. It's all to play for. So I don't feel that I can foresee where that's going. It's really worth looking at. Again, one shouldn't underestimate the difficulties in auto-fixing really difficult bugs where a single cause might not be obvious.
Okay. Now coming maybe two related questions. One is asked by Puyan. Are there challenge problems that you would like academia to look at? And then the related one was whether your tools are open source and maybe how people could contribute or how they can access and try them out.
Yeah, the tools are open source. Check out fbinfer.com. They're actually used in some other companies, and we do collaborations with academics. So go ahead and look at that. Problems that I would like people to work on. I mentioned incremental analysis. Let me just change tack and talk about another favorite problem of mine. And this is what I call pay-as-you-go verification. So one problem in making verification feasible in practice is that it's a pay upfront model. So usually we spend loads and loads and loads of time specifying dependencies, and then loads and loads and loads of time, quotes, proving a program, and then we celebrate. And so after the decision to do it, it's a long way down the road that there's some payoff. Now, if I compare it to testing, although there is a startup cost in testing, testing has more of a pay-as-you-go model, where you do a little bit of work on the testing, you get a little bit of benefit. You don't get the ultimate benefit, but you do a little bit more work, more tests, more benefit. And so for verification to be something that can be deployed incrementally in a gradual way, I think we need an approach to it where the aim should be there's a pay-as-you-go model. Put a little bit of effort in, get a little bit of benefit back, benefit that could be communicated to the programmers, to executives, and so on. And so there will be technical things that should feed in to solving pay-as-you-go if it's possible. And so I just say pay-as-you-go is the ultimate aim to shoot for in order to have engineering artifacts that can be deployed more realistically to more programmers. So that's a great problem. Pay-as-you-go verification, not easy.
Okay, thank you. Thank you. I'm getting a follow-up question. Sorry, first I got the bug report that the names I'm reading may be wrong. So we have a bug in our online platform. I apologize then. I will not read any names. What is the relationship between pay-as-you-go and incremental verification? Is it one and the same, or are there other ways to achieve pay-as-you-go?
Well, incremental verification isn't quite pay-as-you-go because you have to, there's the startup cost. So first you specify loads and loads and loads and loads of stuff, and then maybe you change the proof in an incremental way. So I think we need to be incremental, but I don't think it achieves it. We want to be able to get started on the code base for a low cost. But it's, my opinions here could be wrong too. Maybe somebody can demonstrate the benefit of a pay-as-you-go model that goes against everything I say. in which case it would be great. But I don't think incrementality alone solves it. And by the way, there's hardly any incremental out there.
Okay, so just a follow-up question. Sorry, you mentioned the URL for the tools. I guess people did not catch it up. Can you please repeat it a bit slower? I guess they want it now. They don't want to watch the video later.
No problem,
this will be all available publicly.
fbinfer.com. You see, I'm still a theorist. I have a floor-to-ceiling blackboard in my home office.
That's
fbinfer.com.
Yeah, it's very good having the blackboard and chalk. Yes, yes, you have to prove that you're a theorist. They've also asked specifically about thread-safe. Is the thread-safe tool also included in that, or
that's one of the components of Infer called RacerD, RACERD, and in the Infer repo there will be ways to call Infer and only see the thread-safe bugs. There's a flag called ---- thread-safe-d only, or no, ---- RacerD only. And so once you look at the Infer website, you'll find a way to see what the bugs are, what the bug types are, and you'll find a way to run Infer and stuff like that.
Okay. Yes, we're getting some comments about the blackboards and chalk and the theorists, but okay. Let's see. So this is finishing more or less what we had from the audience. I have questions of my own. I don't know how much time you want to spend with us. You want to stay for a few more minutes, or?
Let's make it 5 more minutes or so.
5 more minutes. Okay, people should feel free to ask questions. I can stop mine and switch to theirs and give them priority. One thing is whether you have some tracking of the rate of bugs found and fixed over time. Could it be the case maybe developers get somewhat sloppy when they have this kind of safety net of Infer, and just like they say, okay, well, if I have bug, it's going to be caught by something else. Is this rate going up, down? Is it staying the same?
Yeah, the thing is, we do track all those things, but it's hard to make inferences about it because there's no control. So Infer is mutating while the code bases are mutating, right? Because we're developing it incrementally or in response to the developers, and it's changing all the time. So we do observe these things, but it's hard to make inferences about them for the reason I said. And we haven't seen, I've not observed them getting more sloppy because of it. They might have done, but I haven't observed it.
Okay. Next question is also from me. This is something I usually like to ask students whenever they present some results in terms of the absolute number. I ask them on a relative basis how important that is. So you showed these 100,000 bugs fixed, and that's definitely impressive just as the large absolute number. But how does that compare maybe to the total number of bugs fixed? Is this closer to 90%? Is it closer to 10%? I understand this may be also very hard to estimate because you don't know exactly what developers are doing, in what other ways they find bugs, how they fix them before commits, after you run static analysis, dynamic, but at least some kind of a hint, like how many do you think you are finding?
Finding a lot. I think that, the thing that, again, it's some number of, say, null pointer exceptions get through. And some are caught by the tool. And measuring those numbers that get through and are caught later, and I don't actually know the number. I think that for some of the things like null pointer exceptions, I think we're fixing a larger number of reports than occur, unique ones that occur in practice. I think that that's true. But the ones that we're fixing are potential bugs, not necessarily real bugs, because they're static, right? Same thing in thread safety. These 2.5K data race reports fixed, we don't know that they would occur in practice. And so in the case of data races, we found 100% of them. In the case of null pointer exceptions, I could be wrong, but I think we're finding a high percent of them. In terms of performance regressions, I just don't know. And it's going to go down for other bug types. It depends on the bug type.
Okay, thank you. I have only one final question. The audience tells me we should let you go. Just one final, very final. It comes from me. But basically, what do you see as the future of static analysis in general? maybe infer in particular, I would like to point out a bit of that kind of what is the history of static analysis in companies. Once upon a time, I was a PhD student and started looking into some of that static analysis at these late 90s. There were these things from Microsoft that were kind of gaining some adoption and traction. Prefix, Prefast, I guess John Pinkins and the others who worked on that. But from what I know, they just completely fall out of use. Is it just somehow that, you know, people get better training and stop making those bugs, or does the rate of false positives go up kind of as my code gets more mature and presumably it's better? If you look into history of somehow applications of static analysis, what do you think about future? Will infer be there in say 10, 20, 30 years? Will it be
I don't know if infer will, but infer's deployment, his fast deployment model will be. And the diff time deployment model is, I think, a big difference. Like, let me never say anything that can be construed in a negative way about that great Microsoft work, but what I understand is that this whole CI world, continuous integration world, and automatic and the code review wasn't necessarily happening in those days, right? So that part of we've hooked in with that part of software engineering, and it makes a huge difference that we're just a bot helping the programmers. And so infer might or might not, the specific tool might or might not exist, but the ideas that it's put forward there are similar learnings have happened at Google, right? There's a great Google static analysis paper, CICM2, that made similar comments about the importance of code review time commenting. And now we're seeing that spread to many more companies. That's spreading to many more companies. And so static analysis feels like it's sticking this time. It's sticking. And I think it's sticking because it's deployed with the programmers in a way that's easier for the programmers. It's not this separate thing that constrains them. So my instinct is that it's here to stay for the foreseeable future and even to expand. But that doesn't comment on any given particular tool, right? Particular tools can be replaced. So.
Okay, thank you very much. So I guess with this note, static analysis is here to stay with us. We can finish. Thank you very much for your talk. Jane would also like to, I believe, come here and express thanks in person. Jane, are you here?
Yes, I'm here. Thank you. I actually meant offline, but thank you. Really appreciated your talk.
Okay. Thanks very much.
Thank you, everyone. I would just like to remind the audience that we have now the third hour. We have a lot of interesting events coming up. Let me just check the schedule. We have the SRC presentations, research posters, cultural exchange. You can meet Microsoft, and you can also meet Facebook. For students who want to get a job there, there will be an event for that. Thank you, Peter, and this closes our keynote session. Thank you very much, everyone.